Hello, in this video we're going to continue in section 5.3 by looking at some basic exponential functions. Now we're going to define a basic exponential function as one that's written in the form f of x equals a to the x, and a is some number that's greater than 0. So an example of this has been the one we did in the previous one with the moon problem. I wrote down a problem where it doubled. So f of x equals 2 to the x. That's a doubling one. We're going to take a look at that one as our first example here. So let's do a chart of values here. So 2 to the x power. So we're going to start off with some positive ones here and do what that is. 2 to the 0 power, anything to the 0 power, we're going to start right here is 1. So 1 will go here in the chart. 2 to the first power is 2, and we're doubling each time. So we double and we get 4, we double and we get 8. So each time, this is exponential, it's 2 times as much each time. So it means as we go backwards, we're dividing by 2. We can see a pattern. So that means this one's going to be 1/2. We divide it by 2. If we divide 1/2 by 2, that's going to be 1/4. Half of a half is 1/4, and a half of a fourth is an eighth. If you notice the pattern here, each of these are reciprocals of one another. If we go from 3 to -3, they're reciprocals. That's what the exponent of a negative exponent does. It takes the reciprocal of the value with the positive exponent. So you can see these are all reciprocals of one another because of that. All right, now let's take a look at the graph of this. So we graph this. So starting out with -3 and 1/8 would be close to that value. -2 is a quarter, half, a 1, 2, a 4, 1, 2, 3, 4, and 8. I believe that's here. So my graph is going to look like this. Very close to the axis, very close to the axis, very close to the axis, and then it turns and goes up and continues to go up this way. So this is my graph of this exponential function, this basic exponential function. And if we look at the graph, we can write some properties down here of the graph. For example, the domain. So the domain of this function, what it looks like, is all real numbers. The range of this function looks like it's everything greater than 0. So f of x has to be greater than 0 here for the range. As we look at, it has an asymptote. It has a asymptote at y equals 0, or the x-axis. It has some value. So as x, so what we're saying here is that as x goes to -infinity here, then f of x goes to 0. As x goes to positive infinity, then f of x goes to positive infinity. It goes up forever. But we have these bound, what's happened at on the boundaries. As we go left and right forever. Okay, so it's always positive. It has an asymptote at the axis. Its domain is all real numbers. It has some boundaries here. We approach 0 here. It always looks like this curve turning upward. So those are some of our properties of exponential functions. Now we're going to change our thing, and we're just going to do the reciprocal function. So we're going to take the function as 1/2 to the x power. All right, so that's the reciprocal function. We're going to take a look at that. So this is called exponential growth. Because it increases. As x gets larger, it gets larger. The values of f of x get larger as the x values get larger. So we have a growth model in that example. Now in the second example we're going to do is going to be a reversal of that. So starting off with the positives again, we know anything to the 0 power is 1, and then first power is going to be 1/2, and to the second power is 1/2 times 1/2, which is 1/4, and then we're going to multiply by 1/2 again and get 1/8. Remember what I said up above, that the negatives are the reciprocal, so that means this is going to be 2. It's going to be the reciprocal of this one. The reciprocal of 1/4 is 4. The reciprocal of 1/8 is 8. So since we put the reciprocal in here, our chart comes out as a reciprocal. It does the opposite. It decreases instead of increasing. So this is going to be a decay function. So we're still going to do the same thing here. We're going to plot some points. So -3 is 8. -2 is 4. 2, 3, 4. -1 is 2. We have a 0 is 1. 1/2. 1/4. 1/8. So our graph comes down from high above and then turns and gets close to 0 here. So we'll get close to 0 on that axis there. So it decreases instead of increasing. But it looks like it crossed in the same spot here. So our x-intercept here above here, this is our x-intercept on this one. This is our x-intercept, 0, 1. Is the same down here. We have the same x-intercept down here, 0, 1. That's going to occur on all basic functions because we're going to raise it to the 0 power and we're going to get 1. So let's look at the domain of range on this one. So domain is still all real numbers. We can plug anything we want in there. The range is the same. It's going to be greater than 0. It's above the x-axis. Our asymptote is still y equals 0, and we still have, or x-axis, that's what we set up above, and we still have some boundaries here. Now on this one the boundaries are going to change. So as x goes to negative infinity, we're going to have f of x going to infinity. And as x goes to positive infinity, f of x is going to go to 0. So as we travel to the right here, we get close to 0. As we travel to the left, we're just going to go up and up and up on the graph as we travel to the left. This one is called decay because the graph is decreasing. So if we're talking about exponential decay, then we're going to be talking about a number for a that's less than 1. So a here is going to be less than 1 to get decay. Up here, to get growth, we're going to have a is greater than 1. So if a number is bigger than 1, it's going to look like this. And if it's less than 1, it's going to look like that. So if we want to summarize that, every time we do this, that's what's going to happen. Okay. So that's the basic graphs. On the next video, we're going to talk a little bit about having these change. We're going to do some transformations on this graph. So we're going to transform the graph. We're going to move it up and down, right and left, flip it over the axes, and change the y-intercept. In this case, the y-intercept is always 1. We have no x-intercepts. None. No x-intercepts. So you want to write that down here. No x-intercepts. On a basic graph, there's no x-intercepts because there's an asymptote on the x-axis. All right. Questions? You can send me an email.